Okay, new video. Okay, so now that we got our sensors, oh, so I need to do a new one, right? Because I want to keep that. Okay, so we'll start easy, obviously. Okay, we're not going to go crazy here. Yeah, the computer is a bit slow here, it shows. Come on. Okay. So which sensor from that list? I'd like to play with two sensors. So I'd like to do something with two of them. So which two are we using? And I'd like to keep it simple, okay? So we're not going to use the ultrasonic nor the PIR, okay? We're just going to read a simple, right? So it's probably a good idea to start with, so say we could take, we could read the temperature. That's not too difficult. And we could use this one. A tilt sensor, that's a sensor. That's a very easy one. It's just a ball inside that's, if it's tilted to the left, say I rotate it this way, right? So the ball inside will go to one side. And so I don't know by heart, it probably goes open. So basically the ball has to be right in the middle for this to become a closed switch. Does that make sense? So it will only become a short if it's horizontal. Okay, could play with one of those. Listen, like, I don't want to spend too much time on just deciding this. We could just use as well, just to start, right? We could use a push button. Okay, so what is our little robot going to read, basically? Do we need to talk about outputs now? That's my question. Do we need to think about outputs now? Like piezo, LED, a little motor, vibration motor. That's the you know, on your phone when you receive either a message or, like, you can turn it off, turn it on, right? Like, it can vibrate basically instead of hearing it, right? So that's what it is. Inside there's a motor spinning and it creates vibration, right? So that's what that is. Those must be new here. Wow, we could have a bunch of stuff circling around. Ooh. Wow, you guys would love that. Yeah, could do something on this here. Oh, that would be a nice one here, of course. Now this one's really advanced. It's doable. It's doable. I'd like some of you to challenge yourself to try that one out by the end of week. Okay. All right. Okay. So can you guys just talk with me here? So what are we doing, right? So when it gets too hot and a switch is turned on, an alarm goes on, and a light. I don't know. I'm just saying stuff here. Is that something we do? Is that a plan? So if it's too hot and the door opens, say to a fridge, right? So I know you could. I know this is not really a robot. I get that, but it's the same principles. There's nothing different. The only difference is you move stuff with a robot. Instead of just making noise, you're going to turn on a motor. That's the only difference. Right? So instead of making sound, you swap it for a motor. And then there's a mechanical component involved. Okay? Okay, so... Can you guys? Fair enough. I was. Okay, can you guys talk to me? Like, is that a plan? Is that something we do? Is someone still here? Hello? Okay, that'd be great to hear if...
I'm here.
Okay, Hassan, thank you for for volunteering. Thank you. Okay, guys, come on. It's just a quick... Like, it feels odd, right? Like, talking, and it's like talking to my screen, okay? All right, thank you. Okay. All right, so how about we do that? Okay, so if a door opens and the temperature is too high, okay, so this will delete. Okay, we'll buzz. And I'd like you guys to do a project with this thing here, okay, because it's kind of cool. And then we'll also turn on the LED. All right. Okay, so Arduino to the rescue. Ooh. Okay. So what are we going to do? Where do we plug those things? Where do we start? So this needs to go, like, we'll need to wire something, and so where do we put it? And this guy here, where do we put that? And then this guy, where does it go? And this. Okay, so help me out.
Wouldn't the temperature have to go into a digital one because it's giving out like a digital signal, I assume?
I don't
think... Or is that one an analog signal because it's like...
It is an analog. Okay, so that's a wrong guess. It's a good try. Okay, so this one, okay, so the temperature sensor, okay, so that's good that they give us what they based it off. So TMP36. Okay, there's a lot of electronics out there. I sure don't know them all. Okay, data sheet. Okay, seriously, share this instead and it just disappeared. It's really driving me nuts. Okay, here, right. So it's a chip well known out there. Okay. What I want to see personally is just the output. Okay, so some kind of graph, something like this. Guys, I'm literally showing you how I would do it. Okay, and so, okay, so there you go. So this is, like, if you don't like math and you're going in engineering, physics, any kind of tech field, yeah, math is everywhere, guys. The minute you touch the minute you touch anything tech, math is there. This is math, of course. So TMP36, this is the right one. Let's just go on that page, right, to get a bit more info. Okay, so it's a tiny thing. It's just the size of a transistor. Okay, so that's what I wanted to know, the voltage range. Okay, so it goes all the way to 5 and ground, and look, it says analog. Well, of course it's going to be analog, though. I want you guys to think about... Oh, sorry, you guys can't see this. Ugh. Hate that. Okay, you know what? I'll share my screen, but if I share my screen... How about I share the window? Okay, so this one. All right. Right. So, sorry, that's what I was seeing. Okay, so TMP36. So it's really small. Okay, so what I wanted to see was the voltage range. So we need ground, we need 5 volts, and we need an analog out. And what I was going to say is, of course, it's going to be analog, because if you look at this here, right? Let's find that chart because it's coming from that page. Okay, it's tinier, right? And so as the temperature changes, right, the voltage, the output changes, right? So you see that? And so we're going to read that voltage on the analog input. So this is what we'll do, okay? So we can wire this guy now, okay? So we can wire this. So it said analog, right? So let's just move that. Hey, you guys can do this as I'm doing it, right? Like your thing will be done, right? Feel free. Okay, we're going to rotate, so Shift R. Okay. Shift R. Okay, so the output is middle. How about we ship it to A0, just to make it simple. This is power, so this is your 5 volts. Okay, so I'll just spin the wires like this to make it a bit clean, right? Don't do just straight lines when you're crossing over. Like, keep it kind of neat. Okay, this is our ground, so that's easy. Ground. Okay, our temperature sensor is wired. Does that make sense? Easy enough, right? You see that middle pin? That's the out, but it's going into the in, right? Makes sense. Out.
Wait, sir?
Go ahead.
So we have 2 grounds. How come you put it in the second ground and not the first?
No, it's okay. That's the kind of stuff I don't want you guys to fall in, okay? Like, this is,
okay.
As we say in French, it's like tripping over the flowers on the carpet, okay? like this is just the same signal, right? Like, I could have, but why do you think they gave 2, right? And why is there 1 at the top here? Well, that's because, do you think it's often you need to wire stuff to the ground in circuits?
Everything needs to be grounded, right?
But that's it. And so that's why that was Hassan, right?
Yeah.
You're right. So that's why the board is providing you with more than 1. But don't trip over this, okay? It's just the same pin, the same output or input. Like, you can see it both ways here. Got that? It helps when I got feedback. Are we good?
Yeah.
All right. Okay, so our temperature sensor here should work. I don't see this not working, but I mean, we never know, right? So you never say you got it until you hit, like, it's the same in a real project. Like, experience just helps you to build with more certainty that it will work at the end, but there's never any guarantee, because maybe the chip is dead. Like, I mean, in real life, this this one can't die. Obviously, it's virtual, right? But in real life, you never know. Wire can be faulty. Sometimes wires are broken inside. Have fun finding that. It's no fun, right? Like, we've had it all, right? In FRC, we've seen all kinds of issues. Then once that was me. Right, like I was retightening a sprocket inside of that's a long time ago. It's like 4 years now, 3 years ago, or is it 2? I forget. But anyway, like, yeah, and I snapped the sprocket, and it was inside, super deep inside the robot. We spent at least 3 hours dismantling, and it was at the competition. And because we had opened everything, our next matches, we couldn't climb as well as we used to. Like, so we just, I'm not going to say the F word, but we just messed it all up. It was really frustrating, right? So you never know. Like, it's easy, a virtual project, it's easy because the stuff is a simulation. But it's when you get in real life that, it just gives me cold sweats just thinking about it, right? And so, anyway, there's tricks to minimize all kinds of issues, right? So you can have, anything can go wrong. You just don't know, right? That's why cars like Toyotas, I'm just giving an example, like that's why they have this reputation, because to make cars like those cars to barely ever break, I mean, it's not a lie, okay? They are more reliable. Like the know-how that goes into making cars like Toyotas versus, sorry for all the Beamer fans here, but versus Beamer, like, anyway, it's complicated making good cars. It is, right? So there's a lot of expertise that go in that. Okay, so the example is more related than it looks, okay? All right, so temperature. Do you have a comments question? Quick. Like, it's way more fun when we have a small discussion going. You feel free to interrupt me. Okay. This one should be easy, right? The push button. How do we wire this guy?
It would go in digital pins.
Yes.
And it could be either on or off.
Exactly. So this one needs to go to digital. But we're going to have to be careful. I talked about it in my video last week. We're going to have to put a either a pull up or a pull down resistor. Okay, we'll show it like now. Okay, so just because it makes no difference, I'll just plunk it right here. It makes no difference. I'm just being lazy here. Okay. So let's take this and go to 5 volts. I'll go all the way around, right? So I'll spin it, go around here, and then I can bring it to the same. Now you need the pin has to go red. I don't know if you see that, right? So it looks like I'm in it, but like if it's not red, I'm not in it. Make sense? So it's got to go red, right? And then it changes color. Okay, so this is good to go. So here, if I press on the push button, now notice that these guys they're no fun to play with, the push buttons, okay? Because they're not clear which side is... Oh, shoot. Even now I'm having a doubt. Oh, I seriously hate those guys. They're really have to... Hold on. We need to shift rotate. So if I base myself off the number, so it says terminal 2 and terminal 1. Okay, so it's got to be this way. Okay, so I was wrong. Okay, so make sure you look at their shape correctly. They're really stupid to work with. The way they're labeled makes it really difficult to guess. So that should work this way. So you got to go terminal 2 to 1, because otherwise this is just common. Okay, so this pin and this pin are just the same. So it just has 2 pins on each side, but it's the same switch, if that makes sense, inside. Okay, so you can turn on and off 2 signal. You can send 2 signals here at once, if that makes sense. Okay. So here, 5 volts. Right? Are we good? Okay, so that should be good. So when I push on the push button, I'll have 5 volts. All right? There's a problem is when I'm not pushing, I need to read a ground at pin 13 or 10, like, right? Because that's common here now. So let's use ground. So I need a resistor. So that's your pull. So we're pulling down. Okay. So what it does is you just go here. That will look ugly, but because these 2 are common, okay, let's just play it safe. We'll go straight to 13, okay? Okay, so you see what I'm doing? I'm using the resistor to just connect that pin to the ground. Now I need to change the value of my resistor. 1K is low, because you don't want it to be high current. You just want it to be the lowest that... that's sufficient, basically. But too low won't be good, right? 10K 5K is good, 10K is good, right? So the color changes instantly, right? I don't know if you saw that, right? So it's good to go. So this is a pull down. So what that does is when I'm not pushing on the push button, which then would give me 5 volts, I need the input to have a signal being 0, being a ground. But if I don't put a resistor and I just wire ground to this pin, I can't do that because when I push on my push button, now I'm going to short 5 volts to ground, and my chip's just going to die. Like, not die like because it's destroyed. Die because the power is shorted. So, you interrupt me, guys, if that makes no sense. Okay, I'm trying to take all my time here. That's the best I can say, right? So you need a resistor here, because otherwise you're going to short your power and the board will die. Like, it will just so the team that was playing on, that was doing brownouts, that was talking about power, right? I requested that you talk about brownouts. I mean, because it's a robotics focus class, that's something that you need to be careful in robots of the FRC kind. So a brownout, what that is, because when you put a motor, right, and you turn it on, depending on the kind of motor, those motors can draw a ton of current, and your battery is not infinite. Like, it's a real battery, and they're kind of small. And that kind of robotics projects, they're still dangerous, right? But they're not the size of a car battery. That would be too heavy. And what happens, Ewan probably remembers changing them, right? And then what happens is, if you have a motor that stalls, so say you have an arm or a shooter, whatever it is, and the mechanism is stuck, but the motor still turns on. The motor, if it turns on and it's stuck, okay, it's going the power going through that will be quite high, and it will create a brownout. So what a brownout is when there's too much current drawn, the voltage cannot stay steady enough, and then it will drop below a certain threshold. So say like an FRC robot, it works on 12 volts, and so a brownout would occur, I'm going by memory, right? Probably at 8 volts, it's starting to go in danger zone. So if your motor stalls and you still ask it to spin, it will just keep dropping the voltage because the current is too high that's being drawn. And then what happens is the board, your brain of your robot, if the voltage drops below a certain level, the board stops working simply because the volts are not high enough. And so brownouts are a big deal. Every team that's worth their salt, that they're checking for brownouts constantly in a real game, because otherwise you'll have random issues and then you'll wonder why. Like, the first year we did well, right? Like, I was still learning, right? Because there's so much to learn in robotics. We lost like our quarter final at Ryerson because of issues like that. Right? Because it's a huge project, right? There's so much going on, right? Alliances and then whatnot, and then since you're a rookie team, right? Like, you're still learning new tricks, right? So these are things like, now I know, right? Like, if we were to redo it, I would definitely be super hard on that, checking for that kind of power issues. It literally cost us a nice, at least a semi, because we were going to win that quarter. That was really frustrating. Okay, what are we doing? Here, sorry. Okay, so this is good to go. Okay, so piezo, what kind of output are we going to plug that in? That's a tricky one. I'm sure I'll trick some of you. So it creates sound, right? Oh, Actually, I'm not going to trick much of anyone because there's just one kind of output. Right? I was thinking some of you were going to say analog, but it's just analog in. So you can't put that into an in because that's an output, right? So that's nonsense. Right? So this is just digital. So this thing, whichever pin will go 7, it doesn't matter. And then this goes to ground. Okay, so how about I go across like this, ground. See what I did here? Okay, so this works. No resistor. Those guys, they operate straight on your output. Okay, it's safe. They use very little current, and so those are the beeps that like your microwave does, basically. Right, so the kind of electronic sound, right? I'm just thinking, do both, right? Like my 2 vehicles that I have, right? Like when I lock the doors, right, using the key fob, right? This is the kind of noise that those make. Like not the horn, right? Not the right? Like some cars make a bleep, right? Like that's electronic key, right? And that's it's got to be a piezo. Maybe they put a speaker, but I would be surprised, and so on. Okay. So piezos are used everywhere. Oh, your oven, right? You know, like when your oven is done cooking, right? Say it was on a timer, right? This is the kind of noise, right? Like click, right? Okay. LED, we'll put it on one of those as well. So remember. Okay, so these are crucial things. Remember the notch here. The notch cathode needs to go to the ground. So we'll cheat. We'll rotate it. Well, we'll rotate it. Okay, you see the notch? Notch now is at my top here. Why am I doing that? It's because I'll connect that to the ground here. So see, I messed up here. So it's got to turn red. And then you click. Make sense? And we'll put a resistor here in line, right? I might have to move my stuff. It's too tight. Oh, like this. Okay, let's go 3, right? Connect that. What's my resistance? 1K, that's too high. 250, right? So 0.25, right? So that'll be 250 ohms. You see the colors changed. So is this working? I think it's all good. Right? It's connected. Perfect. So you have to be careful because sometimes Tinkercad, right? That's why I'm telling you wait until it turns red to let go of your wire, because otherwise it will look like it's connected, but it's not. Make sense? Okay, so it's like in real life. Like if your joint is not done well, your circuit, like that part of the circuit is useless. Okay, we got everything connected. Okay, so talk to me. Like, there's nothing difficult here. And yet...
what was the resistance value for the...
diode?
No, for the one for the LED, yeah.
For the LED. So, you keep in mind... hold on, I'm blanking here. It's 20 mils. So max current LED, the typical value is 20 mils, right? You could, that's getting high though. So 10 milliamps is kind of the ballpark number. That's a small current, 15 mils, right? And this is why, guys, I think I shared that in class. Like, some students in the class, when they're using their black box, they just go like, ooh, a light, right? Ooh, right? And then they take it and then they go straight on the battery, straight on the Arduino, whatever. It's fun, whatever, right? And then next thing they know, well, they don't know, but that's why they don't care, right? The kid next class or next semester that picks up box, say, 15, right? Whatever, whoever is box 15, right? And then they go through all the LEDs and they're all dead. Literally, I've seen it. Every semester it happens, right? That's because the kid last semester, or the class in the morning, say, right, when they were doing a certain project, they didn't remember, because I always explain that carefully. And so they were like, "Woo, I can just." That's why I don't like when you guys, when we're in class, you just take parts and you go like, "Woo, I can put the woo," right? Like, I can, like, that's not for playing, right? That's how we break stuff, right? Okay, so we need 15 mils. So say, right? So our chip works at 5 volts, right? So you do Ohm's law, so it's super simple, right? So Ohm's law, I'm just typing it up because it's faster for us. So Ohm's law, V equals RI, right? Triangle from hell, hate this thing, right? We're looking for R, right? So R equals V over I. I shouldn't even show this. Like, this is so bad. The triangle, like, there's a few that, well, for sure Pranav knows that, but anyway. I hate this drawing. This is the dumbest invention, okay? It's supposed to help kids, and kids that don't get it, they just don't get it even more, right? So this is a very useless trick. Don't use that. Anyway, for what it's worth. Okay, so we need to do V over I, right? So we said 5 volts divide by 0.015, 0.0 I meant, right? Right, because 15 milliamps, that's how you write it. Right, so that's 333 ohms, right? So I was putting 250, right? So, but it's all good. So, well, this one, where is it gone? Here. So I could put, but 25, it will make it a bit brighter, basically. So we'll see it, because otherwise it'll be kind of dim, right? So that it's a ballpark, Pranav, okay? So there's no exact value. Sorry, there's no exact value here. It's the ballpark. And often in electronics, there's a lot of stuff like that. Like, it's not about getting the perfect number. It's getting it in the right range. Okay? And depending on your goals. Okay.
Got it.
Makes sense, right?
Yeah.
Okay. So say that you're making a circuit that you want to last forever on a battery. What are you going to want to do with that resistor's value, Pranav?
Then you get like the exact one if you want it to last forever.
No, you get the higher value possible. You get the highest value possible to limit the current the most, but still get some illumination. Does that make sense?
Yeah, so like there's no risk when it lasts that long.
Well, the point is just to draw the less possible, right, from your battery, right? So in your phones, for example, do you think they rate because there are resistors in line with your LEDs on your phones? There's LEDs on your phones, guys. You know that green light says charging or whatever, right? Depending on the phones. And then, like, those are everywhere, right? But if it's like a microwave where you're hooked up onto the wall, does it make a difference to have the LED a bit brighter than it really could, right? You see the point, right? Like, so
yeah.
It depends on your situation, and this is engineering. It depends what you're doing, and that's where it gets interesting. Like the Apollo missions, right? Like they had certain sets of parameters, and they had to play within those, but a different set of circumstances would dictate different, like approaches and values. And this is the beauty of that stuff, right? It's really an art. It really is. Anyway. All right. Well, we are ready to code. So, but I'm looking at my time, and it took all, it took 30, 40 minutes. So, so I guess what I'll do, I'll keep recording. What's our official time? Hold on. 38. So listen, if you guys want to go and whatever, I'll keep recording, okay? So there's no point me shutting down the meet, because if you have questions, I'm happy to take them. How's that, folks?
Sounds good.
Right, so I'm going to finish this. I'm going to code it, right? It might take me 30 minutes. I don't know. But, like, I was talking a lot here, right? So that's kind of why I'm taking forever. But feel free to interrupt me. Like, it's just more fun, and you learn more. You really do, okay? All right, so if you feel like you've got enough or whatever, you need to go, whatever, okay? So wish you a good evening. Okay, so I'm going to finish here. All right. All right. So, comments, questions before we go coding. Any doubts? Any?
Is there so is there like a specifically different code for like every single like sensor, or is it just like the same but then you just have to know like the analog signal for each of them?
That's a good question. These two here. Oh, I just thought of something. Oh, why didn't I think of that? These two here. It's kind of redundant here to have them separate. We could technically put them just in parallel on the same output. That wouldn't work if we want... Actually, let's do that, okay? We'll have the piezo to beep when it's fault, right? When it falls into fault, right? So too high to too hot, say, and the door is open, whatever, right? And we'll have the LED to be on when it's safe, when it's not in fault, if that makes sense, right? So to use the two outputs here. So on the digital, it's super easy, okay? Here we'll just digital right pin 7, and here we'll just digital right pin 3. And we'll literally just actually, I already can see in my mind, we'll just invert the signal. So using the exclamation mark that I used last class, right? When Ewan has heard that many times, I don't know if he's still there, but I really believe this is one of the most important things when you do any kind of projects like that. And I sure said it a lot during the FRC build time and all of that. But the dumbest solution always works, right? And so is the best. And you have to find ways when you code, and I'm talking to all of you guys, those of you going in computer science, there's got to be a couple in here. If you want to impress your employers and so on, it's not about making just a lot of work for yourself. That's not smart, okay? Like it's about finding the fastest, most efficient way to get it done, right? And I was huge on that when we were doing the FRC, and yeah, and I still remember some comments from some teams going like, wow, like this is so easy the way you guys are doing this, and yet we were getting the job done, right? And I remember getting comments like that, right? And we saved ourselves so much hassle, right? So that's kind of why that exclamation mark, like you want to know all the tricks you can, okay? So when we get to the code, like that section, I'll explain. This here will just be read, right? So it's very simple. Now this part here, we're going to have to fiddle with it, okay? So from what I saw here, we're going to have to determine what's the cutoff voltage, basically. Okay, we might have to do a bit of math here, okay, which is super easy. Okay, so how about we get going? Okay, because there's quite a bit of stuff to do here. Okie-do. Code time. Oh, I didn't say to start. I meant code. All right, so you're not using blocks, right? Because we're too big. We're doing it in C. Okay, so you always define your ins, outs, right, before you dig in, right? That's for sure, right? Like, you don't start your code and starting whatever, right? Like, you go in sequence, right? So define your ins, define your outs, and then start coding. All right, so pin mode. So 13, that's this one, right? That's a in. So we change that. Right? You guys should do it right now, right? Like you'll have your whole thing done. Okay, that's input. Okay, easy enough. Okay, so you see here A0. Okay, so we don't need to define it because it's configured already as an in. Okay, so we're fine. But we need to copy paste this twice because of pin 7 and pin 3. Digital. Do I need to make this bigger, or you guys can see my numbers big enough?
Could you make it like a big, just a bit
Yeah,
bigger?
I could make my whole screen a bit bigger. Hold on. Maybe like this?
That's better, yeah.
But we lost track.
Thank you.
No, well, but we can't see the parts anymore. But anyway, we'll go this way. Okay, so how about I tighten this up here? Okay, this way. Right? We know this works. Okay, that's pretty good. Okay, so we have pin 7. That's an out. So we go out. We got pin 3. That's an out as well. Right? So I need to define those. So 7 and 3. Everything clear? So we're done in setup right now. Okay, so we got our ins and outs defined. All right? Okay, so we can start coding now. Okay, the code proper. I always like, well, it depends, but like this is here that you would declare your, shoot, there's a name escaping me here. Your variables that are overall, basically, that have a scope of all the code. This is where you would declare those variables. And we will likely have a couple here, like input here, right? So let's actually declare one already. So bool, so that's for the door. So how about we call it door, right? It's always a good practice to define it. So let's put it at 0. Semicolon, right? That's how you end statements. Okay, so semicolon, very important. This is C here, right? So you can't avoid that. Let's think about variables. So we'll need a variable for the temperature, right? So that will need to be an integer. You can't use a boolean. So boolean, remember, is true or false. In other words, 1 or 0. Or 5 volts or 0 volts, right? Like these are all equivalent. True, false, 1, 0, 5, 0. I'm missing 1, I think. Okay, it might come back later. But anyway, that's the idea. Okay, so we need an integer for temperature. Let's just call it temp, right? Again, always good to define. So let's define it at 0, but it's going to get changed right away when the code starts. Do we need to define a variable for out? I'm doing it live, guys. Like I haven't tried it yet. Do we need, like we can add variables as we go, so it's not an issue. But it's smart to think about it before you start, like, right? Kind of gives you an idea for your whole code, right? Do we need an out, a variable for the output? I don't think so, because that will just be the result of a logic operation. Okay, that looks good to me. Okay, so we're going to read, right? Digital read from 13. So we don't need this high, the high, right? Now we're going to define that as being door is equal to that. Make sense? So we're reading the value at input 13 and we're assigning it right away to door, the variable door. Easy enough, right? But we need to read the value from A0, right? So now we'll say temp equals, now that's analog read, and then you put in bracket A0, semicolon. Now, again, guys, like, it's not my first circuit, but even myself, I need to confirm. Analog read, Arduino. I always go check your syntax, right? Just to make sure. So you look at an example. So analog read, right? So that's how I'm doing it. So this is good. So that works. Okay. Since we're on that page, we're going to look at the increments. Okay, so this is what we need here. So you see that? 4.9 millivolts per unit. Okay. So the pin A0, right? Let's go back here. So that pin here can read between 0 volts and 5 volts. Okay? And if it's getting 5 volts, A0 here would give me 1024. Does that make sense? Right? I'm just changing my code just so you see it. Right? So if I applied 5 volts to A0, if I do analog read of A0 when it's 5 volts, my number will be 1024, 1023 to be exact. Because it's 1024 values, but it's 1023 because we start at 0. Good to go? If I had a 0 volts, what's my value here? Come on, that's easy. What's my value if I have 0 volt? I'm not checking the chat. You need to talk. If someone's still here.
Would it be 0?
It would be just 0, right? So if I have 0 volt, my range is at the bottom, so it's 0. Right? So 0. Good enough? Right? But here's our challenge. It's not very complicated. Okay, so smart people, try it with me, okay? I'm going to give you 1 or 2 minutes. It's not very hard. Okay? When are we going to declare that that it's dangerous? So how about we say at 0 degrees, right? So the minute that A0 will read less than 0 degrees, that the piezo has, right? So it's basically checking if your fridge is cold enough. Actually, so to be real, we shouldn't say 0. We should say, because real fridges, okay, you guys don't know that because you don't check, but when you're RVing, like, you need to check your fridge, right? So now I know just because I've been checking. So your fridge needs to be at 3 Celsius, roughly. Because when it gets under 0, your milk freezes and your veggies, right? And then it's a mess, right? Because you lose your food, right? So let's say actually 3 degrees Celsius, maybe 4, right? So if it's higher than 4, fridge is too high. We could even make it that it's an RV sensor here for a fridge, where if it's too low, it also beeps, actually. That would be really good, actually. We're switching the specs, but it's actually a really nice. Let's just keep at 4 degrees and higher to beep it. But the worst, in my experience, is when your fridge freezes your food. That's the worst, right? Okay, but anyway, like, we can change it as we go. So temp, that's how we had it. That's good. Okay, so smart people using this here. Okay, so we're going to have to estimate, right? So 4 degrees. Okay, so that would be 12.5, right? Because I'm halving my range. 12.5, half of that. What's that? 6.3. 6.3. So I'm just beneath that, and I am about here. I don't know if you see my cursor. So what's the value? That's about this. So what's that? That's 0.55, I would say. Are you guys agreeing? 0.55. Now, the one thing we haven't checked is it the red one? We need to confirm that. So let's confirm that. Is that? Okay, so I want you guys to find my volts for 4 degrees Celsius. So what's the voltage that we will read? No, sorry, we've done that. Sorry, that's not what I meant. I meant so what's the math value that we're going to read here? So let's put a comment. So 4 volts roughly equal, what did we say? Was 0.55. Oh, 4 degrees, seriously. 4C, right? Is 0.55 volts. Hold on, let's just confirm, because that's not clear to me here. Data sheet, all Arduino. Let's just go check another page. So temperature. So which one are we playing with? TMP 36? Which one is it? TMP 36. So it's B. Okay, so we were using the right chart. So it's B. So it's the red one. So we were using the right one. Okay? All right. Okay, so at 4 Celsius, theoretically, we should get 0.55 volts. Good to go? Now my question is, how much in my A0 input will that read? Can you guys try the math? So 1 minute on this. Try to figure it out. Using this info here, on here, right? So you see this? 4.9 millivolts per, well, they say per unit, per extra step, basically, right? Because it makes this, because that's an ADC, guys, right? Do you remember in class we talked about ADC converter, right? You guys did a graph on that, images, right? This thing, right? So each step here, each step is 4.9 millivolts. So 4.9 millivolts per step. So what's the value we should theoretically read for 0.55 volts? Come on. Because then that will determine our if, right? Our logic structure. Is anyone still paying attention here? Oh, they're all gone. All right. All right. So let's finish that. So 4.9 millivolts. So you just divide, basically, right? So 0.55 divide by that. Right, so let's just type it here. That'll be nicer to copy. So 4.9 millivolts, so that is 0.00049. So that's the math I need to compute. Copy. So that's an estimation of what my A0 input will be. So 112 it said. So 112. Okay, so I don't need that anymore. So 112 roughly. So that's the numeric value I should read at 4 Celsius. Perfect. Next step. Okay, so I guess we'll have to have nested ifs. So if syntax in C. pulling it up to be sure. So copy paste this. Right? Okay, so we need a space in between here. Maybe that's not necessary actually. That's okay. Okay. So if the door opens, that's obviously a fault. So if door equals, now be careful, double equal here because we're evaluating, equals 1. It should work. Then I'll just shut the Google Meet, okay? Because it's making the computer be a bit. Are you guys still watching?
I'm still watching.
Oh, okay then.
I don't know if anyone else is.
Okay, I'm happy then. Okay, perfect, guys. Perfect. You guys are getting it done. That's great. Okay. It's just it feels odd, right? Like I'm talking to people, but I'm really not. Okay. Good. Thank you. So you feel free to interrupt, okay? This is more like it's more interactive. Okay. Okay, so if door is 1, so now door here, we'll put a comment. Door open equals 1, right? So we need to be clear on this, right? Because you could configure a switch on a door to go the other way, right? So there's a bunch of details going on here. Okay, so let's assume that. Yeah, and then we're going to do a digital write on pin 7. Nope. And then we say hi. And then we're going to do digital write on pin 3, right? The LED, right? So how about we have it flipped, right? So we'll go low here, right? Since we're using the 2 outputs, let's just have them do the opposite. Oh, so here's something we could do here, because it's based on door. So here, actually, we could just have... No, we'll leave it like that. There's no point making it more complex. Could make it more complex, but that's okay.
I have a question.
Go ahead.
For after the if statement, why didn't you put the colon, semicolon, right?
Oh, here?
After you did, yeah.
Like here?
Yeah, right there.
Well, because that's not the syntax. If that's why I went to the syntax. I was just confirming because I was pretty sure that was that way. But you see there's no semicolon here.
Oh, okay.
So that's C, guys. Like, so when you do evaluations, like ifs, break, while, a switch case and all of those they don't, well, depending, the switch case is a bit more, it's a bit more involved. Right, so you see the general structure here at the top, no semicolon, but yet in between, so after the breaks, you put semicolon, right? So you just go back on a syntax page. You always need to go check. That's the bottom line. Right, so if I go back to my if-else, right, so this is the general structure. I'll use an else because in this case, it'll be convenient. So we'll go here, else, curly open, where is it? I'm using my French keyboard. It's always a challenge getting that. Okay, how about I go English? Okay, so just make it simpler. Okay, else, well, so this, but flipped, right? Right, so it's just copy paste, but now put that low and then put that high, right? I like to try to keep my stuff lined up. It's just prettier and easier to debug, right? So you see, right? So this here, technically, I would put it in line with this here, right? It's if you have a lot of code, it just makes it easier to read. Okay, you don't need to organize it pretty. Also, I'm missing a closing curly here, right? Because my big void opening curly here, right? I got rid of it, right? So that's why there's two here. Easy to understand. Okay, so that's the door. So that's easy enough. So let's go outside of this if, and then we'll do a new if. We could make them nested, but I don't think there's really a point. Let's see, we can move stuff around later, so it's easy. So my temperature is on A0. And this is temp right now, because it's been red. So if temp equals double equal, because we're evaluating, we're not assigning a value. If temp, oh, we're not doing an equal actually, we're doing a greater or smaller. So if temp is, where's greater? Ha, this is easier on the French one. Let's go back to French. Where is it? Here. So if temp greater than, now this is where we use this 112 here, right? So this is the 112 from the analog read. So we put that here, paste, oh, sorry. So 112, then what? So curly curly, opening curly, put the closing curly now so that you don't forget it. And what we're going to do the same, right? Oh, and I'm seeing here, since we're literally repeating, so I think here what we'll do is we'll say or. So I think that's what we'll do here, right? Because I was just going to repeat all of my digital writes here, right? My digital writes, and it might create funny situations. So we want to clean that code up. So we're not going to use another if. What we'll do is we'll here, instead of having, essentially our machine is supposed to start beeping if the door is open or if the temperature is too high, right? But when is that true? Well, it's when either the door or, that's why I said or, the temperature is meeting a certain criteria. So here we'll put a or. So we'll do double brackets here. We'll cut that off. We'll go here, put a closing bracket. But here we need an operator. So let's look it up. So C operator. I think it's the double line. Or is that? I think it's the double line. I'm just going by memory. Where is it? Okay, hold on. Or C operator is probably simpler. There. Relational, logical, it's or. So it's this one. So it's double straight lines. Okay? So those are super useful operators, guys. So this one, double ampersand, that's ampersand, right? Is that ampersand? Ampersand? It is. Okay? So double ampersand is an and, right? So it's a logical operator. Useful, super useful. Okay, so we're using this one. Let's just copy paste it. Here, right? So now what's going to happen you can embed logical conditions like that, right? So you can check for the door. So if the door is 1, or if the temperature is higher than 112, right, which we read from that input, it's going to go true, which is going to do this here. Well, that looks like it. That's pretty much all we need from what I see. So, oh, here I need to comment this out. Okay, so it's a simple code. There's nothing really special about all of this. Let's just look it up before we hit play. That looks decent to me. Let's see what happens. Okay, so temperature must be too high. So click on this guy and see it's 25 Celsius, right? So let's go down. Oh, there you go. So it seems like we had our value correct. Right, so -3. Can I use my cursor? No. Okay, so see 2, it's fine. Can I go to 3? Right, so jumps at 4, which is when we said to jump. So this works beautifully. So it's cold, so now the light is on saying we're A-okay, right? And then push on the push button, that's the door open. Perfect. Perfect. Wow, okay. Woo! Can still do this. It's always fun when you're done. Good. Comments, questions, guys? Just before we save that. Okay, so we'll log off. I'll post that. And you guys, when you're done, you just submit it on the Google Class. Okay, guys. Have a good evening.
Have a good day, guys. We'll see you tomorrow.
Bye-bye.